Hi, this is Module 29 of Engineering Vibrations 1, an introduction to single degree of freedom systems. And today's learning outcome is to now solve for the natural frequency, damping factor, and time to decay using the logarithmic decrement method for the system we've been looking at that's undergoing rotational motion and free undamped vibration. So here's that suspension system we've modeled. We came up with the DEOM last time. There it is. We have a plot of the actual decay for the actual system that we're modeling. With that DEOM, I can put it in standard form. If you look back, we did this before. This was the standard form by making the coefficient of the acceleration term equal to 1, or unity. And so in this DEOM that we have for this problem, instead of y, our generalized coordinate is theta. And so omega natural lines up with the coefficient in front of the displacement term, and therefore I can solve for the natural frequency. It's just the square root of 3kb squared over ml squared. And so I put in actual values that were given in the problem for k and b and m, and I end up with a natural frequency for this system of 21.2 radians per second. So that's one of our answers. Then I look at the logarithmic decrement so I can come up with a damping factor. Here's the definition of the logarithmic decrement that we came up with for multiple cycles. In this case, I'm looking at 10 cycles. So I have, 9 cycles. I'm going from 1 to 10. So I have 1 over 9 equals the amplitude at the first cycle, which is 0.05 radians, divided by the amplitude of the second or 10th cycle, which is 0.015 radians. And so I get a value for the logarithmic decrement that I've measured experimentally. Then we saw that we could solve for zeta, put those deltas in. There's the numbers. And I find that the damping factor, zeta, for this system, it's underdamped, quite underdamped. It's 0.0213. The third part of the problem was to find the time to decay if we started at 0.1 radians and went to 0.02 radians. And so the time would be the number of cycles that we go through times tau sub d, the damped period of oscillation for each cycle. We know that n, from that top definition up here of the log decrement, n becomes 1 over delta times the natural log of those peak ratios. In this case, I know what delta is. I'm going from a amplitude of 0.1 to 0.02, and so that becomes n of 12.03 cycles. So roughly 12 cycles to decay from 0.1 radians to 0.02 radians. So tau sub d then, we remember, is 2 pi over omega d. And so tau sub d equals, we put in for omega d, omega natural times the square root of 1 minus zeta squared. I can put those values in that I found, and the the damped period of oscillation is 0.296 seconds. Now I can substitute in, I know n is 12.03. That damped period is 0.296 seconds. And so the total time to decay from 0.1 radians to 0.02 radians, you can see how this could have a real practical importance on how quickly a real-world system decays from some value down to another value to meet some sort of a specification. And in this case, for the problem we solved, it's 3.56 seconds. And so that's a great problem that we went through on analyzing real-world systems, even using that technique for design as well. We found the natural frequency, we found the damping factor, we could find the time to decay. All these things are very useful tools in working with engineering systems. And that concludes today's module.